So yesterday we started the public key exchange topic, and we finished up with conclusion that everybody is happy, if you remember. In fact, they're happy for different reasons. We say that Alice and Bob both have their own public key and private key. We just use the sub-index to denote who is the owner of the key. And just to be specific, we use RSA algorithm as our public key encryption scheme. And if we want to support duplex data exchange, we want to make public key of B to be delivered to A and public key of A to be delivered to B. And let me just repeat this. If we deliver them before real message exchange, this information can be intercepted by Kathy, and Kathy actually will block delivery of the original messages and will make a record on public key of Bob, which is present on the wire, and will make a record of public key of Alice. But Kathy also has her own private key and public key. We call it as public key of Kathy and private key of Kathy. So public key of Kathy will be sent to Bob, and it will be sent to Alice as well. After this, Bob will have public key of Kathy, thinking that this is public key of Alice, and Alice will have a record on public key of Kathy while thinking that this is public key of Bob. And now, for example, Alice wants to send to Bob a message. She wants to encrypt this message to support data confidentiality. So Alice will be using RSA algorithm, will put a message, and will use public key of Bob as she thinks she is using public key of Bob. In fact, this will be public key of Kathy. Because that's what she has for the public key of Bob. And this is that direction. And if Bob is going to send a message M2, here also will be using public key of Kathy, but direction of the data exchange will be different. Both of these messages are in fact encrypted with public key of Kathy, and Kathy is the only person who can decrypt those messages. So pretty much Alice and Bob will be thinking that they send data in secret, but reality is different. Kathy can read these messages. And moreover, Kathy, upon intercepting of these original messages, wants to decrypt them. So let us say this is C1 and this is C2. So Kathy intercepted message C1 and message C2. Kathy reconstructs M1 from RSA C1 private key of Kathy, and she reconstructs message M2 by applying RSA algorithm and message C2 private key of Kathy. And then she wants to re-encrypt the messages because she wants Bob to receive the message. Because if Alice and Bob do not receive the messages that they expect, they will suspect something. What Kathy is doing next, Kathy is now using the two public keys that she intercepted previously. And she encrypts C1 star as RSA message M1 public key of Bob, and C2 star as RSA of message M2 public key of Alice. And then she sends that message to Alice and that message to Bob. No, other way around. So Alice, yeah, this one goes to Bob and this one goes to Alice. So this one goes to Bob and this one goes to Alice. So Alice, Bob receive the messages. They can decrypt them because corresponding public keys are used. They read the message, they do not suspect anything, and they just continue message exchange, which can be read by Kathy. How can we fight this situation? We want some matter of authentication. In other words, we want to identify some part of this message exchange which we will not trust without seeing a proof of authenticity. So what parts of the message we want to check, we want to evaluate to be authentic? Probably this. No, not this. This and that. Whatever we receive as we think is public key of another person, here or here, we want to check that this is in fact the public key of that person. How can we check this? We have a digital signature mechanism. How do you think we can use digital signature mechanism if we want to check correctness of public key of Bob here and public key of A here? Obviously that if this is public key of Bob, meaning that Bob is going to sign that something. So if Bob signs that message, which is his public key, we will be able to check the digital signature. But to check digital signature, we need public key of Bob. So once again, if Bob is the signer of that message, which is his public key, then yes, we receive that information with the along with the digital signature. But to be able to check correctness of the digital signature, we need to have a record on correct public key of Bob, which is in that message. So same situation as before, but formulated differently. And here is the problem. We cannot check digital signature without knowing public key, but we know public key only after checking the digital signature. And the same challenge on the Bob side. We've got a public key of A, and if we want to check that this public key came from A wants to apply digital signature to this. It is possible, but digital signature of A, after being applied to the public key, requires public key to validate correctness of the digital signature. And this situation seems to be unsolvable. What do you think is the solution to the problem? Terminate Kathy? Yeah, that will work. But another one will come. Some sort of server. Another, a person whom we trust. A person or entity, and that entity in public key infrastructure, that's the terminology that you want to use in this context. Public key infrastructure. In this environment, that trustable person is called certification agency. You probably have seen this abbreviation in the internet, especially in the context of some website where you can see that a certain website is protected by, for example, VeriSign certification agency. And sometimes they just display a seal or some other form of a proof that this website is protected. But what do we say? How do we understand this concept? A website is protected. The website is not protected. Traffic to that website is protected. In other words, when we want to use the service of that certification agency, we as the clients, we as clients of some service do not ask certification agency to provide us some sort of proof that certain resource is good. For example, if you open up in the web browser some sort of web page, say Facebook. We know Facebook is protected, right? And we see that it is protected. The way how we establish the fact that certain web page is protected, or certain website, better to say, is protected, it is not like we contacting that third-party person from our side. We do not ask CA to prove us that certain website is protected. There is another procedure to that. Because if we simply ask from CA if Facebook is a good resource, whatever response CA sends to us can be crafted by attacker, can be intercepted and modified. So the technology which is used here relies on the presence of certificates. And certificate is what we're going to discuss today. Certificate is a combination of a public key of a person, his name, in other words, identity, and these pieces of information are signed by digital signature of certification agency. Once again, certificate is the public key of some entity. In context of web browser, it will be public key of Facebook website, along with the name, facebook.com. And everything together as one whole entity will be signed by a digital signature of certification agency, of CA. Who is that CA? So CA is a business who offers a service of applying her digital signature to certain public key or to certain certificate. Who are the main consumers or clients of that business? What do you think? Who pays the bills of CA? Those websites who wants to provide the secured service. So Facebook, Gmail, whoever it is. If I, for example, want to establish a server where users will be trusting, I want to buy that service from CA. The way how I buy it, I'm sending to CA my public key, my name. She applies the digital signature on this and gives me certificate. Certificate that later on I put on my website. And pretty much that certificate, it's a file that contains a public key of a website, name, whatever URL used, and some other piece of information which we will consider today. But name and the public key is important. And that certificate is signed by digital signature of CA. What's the function of this certificate? Anybody who is accessing my website now and now this is service of the web browser, before it displays you the web page from that website, web browser contacts my web server and asking for that certificate. So certificate is the first thing to be delivered from web server to web browser. And only upon receiving that certificate, web browser now decides whether or not it wants to display web pages from this website or not to display them. So web browser needs to decide for correctness of that certificate. How can we say that certificate is correct? Digital signature can be validated. That's the condition. Digital signature that is contained in the certificate can be validated. If result of this validation is positive, meaning that certificate was good, meaning that website can be accessed in the secured way. What does it mean we access website in the secured way? We can encrypt sensitive data. And here is the important part. We've got the certificate of that website. Certificate has the public key of that website. We use the public key taken from the certificate to encrypt the data which we want to send to this website. In reality, it's quite different. Nobody's using public key to encrypt the real data. Because, yes. It's what? There is not one. There are many. And we will be talking about this in a moment. But what I'm saying is that public key or RSA algorithm is very inefficient, and you remember how much calculations is required to process RSA data. And we were practicing with real small numbers. So RSA algorithm is not that easy to be applied for each and every piece of information which you're going to exchange with website. Conceptually, we can think that public key of a website is used to encrypt sensitive data. And this is correct assumption just for us to understand the concept of certificates. In fact, public key of web server or website is used to exchange some symmetric key. So later on we use public key to encrypt a symmetric key that later on is used for data encryption. But that's a different story. That's how real web servers work. We're talking about how public keys are being distributed. So before we start using the public key, we want to check digital signature of CA. To check digital signature of CA, what do we need? Public key of CA. Where we have this public key of CA. If CA gives us the public key, this public key can be intercepted. And can be crafted by attacker. So where is the beginning? There is no beginning. But there is a process that helps us to deal with public keys of CAs. James asked the question that how many CAs we have. Let us just assume for a moment that there is just one CA for the entire internet. How many websites we have in the internet? Maybe even more in a couple days. So if there is just one CA, let us say it's a very powerful computer. That powerful computer that can handle all the requests from the website, because website pretty much wants to get the certificate not that oftenly. Usually you buy a service to try the certificate and you're probably interested in just seeing how it works. In this case, you're talking about 1 month trial period. You may consider buying certificate for 1 year, for 3 years, for 5 years, something like this. Let us say we allow every server to purchase a certificate every year. So every year, every certificate needs to purchase, every year, every server needs to purchase a certificate. We have trillions of websites. If we divide it by number of days in the year, assuming that we evenly distribute the requests, we have 365 days in a year, right? Then we divide by number of hours, then we divide by number of minutes, by number of seconds, and you probably will get thousands of requests per second. It's not the worst thing that certification agency needs to have very powerful infrastructure. That's not actually a problem if it runs the entire internet. The problem with a single CA is different. It will be the only entity who decides who can get certificate and who cannot. Because if CA rejects a request to certificate, meaning that this website will have no chance for secret communication. That's one of the main reasons. And the second reason is actually technical. It probably is great infrastructure to issue certificates for all websites in the internet, but think about potential failure of the CA. This is just single point of failure. If it fails, no new certificates. And no new certificates is not actually the biggest issue. Sometimes certificates get hacked. And certificate needs to be reissued. Certificate needs to be revoked. And revocation of certificate, that's another responsibility of CA. So if CA is down and you want to revoke a certificate, you want to mark certain certificate as invalid. That's the function of CA. If CA is down, nobody can say that this certificate is no longer good. People will continue trusting this certificate. People will continue using the compromised public key. What do we understand by compromised public key? What does it mean? A website provides the public key in form of certificate. How do we understand compromised public key? What do you think? But everybody can access certificate, everybody can access the public key. Public keys are not encrypted, they are signed. So everyone using a web browser can access the public key of that website. It is not actually a public key that is compromised. It's a private key which is associated with this public key. And where is this private key? What do you think? Where do we want to keep the private key to benefit from allowing everybody to use the public key? No. If it is at the CA, how we, as the owner of the website, going to benefit from this? What for do we use the private key? The private key of our website? To decrypt the data. So private key, every data which are sent from clients to our website needs to be decrypted, I'm sorry. And it is decrypted by the private key. So we want to keep the private key on a website. And now you should recall all these stories about websites being attacked. Again, what does it mean to attack a website? What we will be practicing next week, it's not attacking of a website. We're not going to come on Facebook. They will definitely not be happy on this. What we will be doing, we'll try to sit in the middle and try to intercept traffic of particular user. They don't care about users that much as they care about their private key. So nobody is going to put us into jail for intercepting some traffic that goes to Facebook. We do not compromise their private key. Private key is their property. They're going to protect it. So private key can be compromised by hacking the website, by attacking the website. Private key is a file stored in a file system on a web server. When hackers attack a website, they get access to that file. They may use all different ways to do this. But if their attack is successful, they get the private key. And now every data this website receives can be decrypted with this private key. Starting from this point, private key is known to be compromised. Private key is associated with the public key for that resource. And now we want to say to everybody in the world, people, if you have my public key, stop using this. That's the process of certificate revocation. Because it is not like a person who is communicating with a Facebook is going to retrieve certificate over and over again. It's better to say for each and every web page of the Facebook, it is not logical to do this. Certificates are retrieved once in a while, and they are retrieved at need. How do we know that certificate needs to be retrieved again? Certificates usually going to be good for a reasonable amount of time. The time that we pay for. So 1 year, every year we want to purchase a certificate. In other words, certificate can get expired. So when we're talking about certificate and we call that certificate invalid or compromised, we want to revoke it. We want to revoke it with the service of CA. and process of certificate revocation, meaning that we tell everybody, stop using the certificate if you have this. So it may happen before the expiration date of certificate. Say everybody knows that certificate for Facebook will be good till next January, but then Facebook get hacked. In this, whoever has that certificate needs to just renew it. But this service is only possible if CA is up and running. As we said, one of the assumptions was that CA can be put down. So that's one of the reasons. We already outlined the two. One of them is that CA is not a monopoly, and the second reason, CA may have technical issues. And there are many other reasons, but not that dramatic ones. So there is no just one CA. There are many. How many? It depends. It's probably not that easy to become a CA, but it is possible. Of course, you want to be approved by some agency, by some institutions, but it is possible that some new business may become a CA-related business. If you want a number, think about 1,000 CAs in the entire world, in the entire internet. If it is 500, probably 700, it's still a reasonable number. I don't know how many. And it's hard to count them. But it is not a million, it is not a billion. It is not 10. It's about 1,000. So the 1,000 CAs, first of all, they make competitors between each other. You can buy a certificate for 1 year from well-known CA like VeriSign. You're probably familiar with this name. That's one of the most expensive certificate. And for 1 year certificate, you will be asked to pay, I don't know, $500 easily. For one certificate, for 1 year, only for one single site, website. If you have a domain, if you own a domain, you might want to run multiple websites on this domain. Say, in our case, we own a domain called gswcm.net. That's where I put all these video tutorials. And here we have many websites. Maybe not that many, but we can have as many as we want. This is called wildcard certificate. So, in other words, I'm not limited in setting up particular certificate. We purchased the wildcard certificate, assuming that we don't need to purchase a separate certificate for each and every website that we have here. That type of certificate from VeriSign for 1 year costs many thousands of dollars. Why this CA is that expensive? Because everybody recognizes that name. If you consider it's actually not the CA which we use. We use some brandless, cheap, somebody who just provides that service. And I think for 3 years we paid like $500 for that certificate. With these guys, we would need to pay thousands. So pretty much you choose where to buy certificates from. And the drawback of this freedom is that whoever you purchase certificate from could be unrecognizable by your potential clients. So in other words, you say you put this certificate on your website, and then here are people with non-standard PCs. but say with Android device. They go to this website and then there is a warning message. The website, the certificate is not good. How this is happening? I purchased certificate, I paid $500 for that. Why my certificate is not good? Because that particular browser doesn't know public key of certificate that I am using. So it is now a problem for each and every certificate in the business to make each and every browser in the world to have their public keys. So how this is possible? How can we make public key of every one of these 1000 CAs to be delivered to every copy of a web browser software on every device, on every computer? You may have multiple browsers, so each must be equipped. Certificates, moreover, can be used with mail services. So delivery of email correspondence also can be protected the same way. Many applications. Web browser is just one of the applications. What would you propose as delivery method for certificates of CA? Also assuming that public key can be, that certificate can be expired. Sometimes it needs to be renewed. Even CA can be attacked, can be hacked. So private key of CA can be compromised. So this is nothing more but yet another certificate which needs to be delivered to everybody. How would you organize such a delivery? Can you say it louder? Another CA? All right, for that CA, how can we? So many CAs. But what about the last one in the chain? Any other proposals? If we cannot just send the public key, we want to send public key with digital signature. Public key of digital signature needs to be validated. To validate digital signature, we need the public key of somebody else. Where can we get that public key of somebody else? So we need to think of some alternative approach to this public key infrastructure to deliver public keys. And the way it works, it's trivial. When you get your web browser, your copy of a web browser, it is equipped with public keys of all that CAs. So in other words, when you install web browser on your system, better even to say when you install operating system on your computer, there is a storage in that operating system. There is directory files in Windows. It is registry. In Unix, that's just particular directory with files. But those certificates of all that CAs are stored there. So in other words, every device in the world has records of the CAs, and those certificates are pre-installed. What if we want to make a change to a certificate? Say, it is time where certificate of VeriSign expired. How can we get this new certificate? Should we reinstall operating system? Updates. That's the key word. But not web browser, because web browser is not the only consumer of certificates. It is what we call security update of operating system. So when we do the update of operating system, we pretty much not only patch all the libraries with the to address vulnerabilities, known vulnerabilities, but part of this process is to retrieve updated versions of certificates if any changes there is needed. So we get the new certificates over and over again if needed. If you do not update your computer, your operating system, for months, for years, then probably we'll lose possibility to communicate with websites, because eventually certificate of CA as stored on your operating system will be expired. With expired certificate, you will not be able to validate public keys of websites, because those public keys will come with certificates of those websites, and those certificates are signed with digital signature of CA. If you want to check, validate digital signature of CA, you want to have its public key. If public key is expired, nothing can be done. All right? That's the same as you change the system clock on your computer. Make it 1 year back. More than likely, many of the certificates in your certificate storage will show expiration. And you will not be able to access Google, Facebook, many other resources. Some of them have actually really long expiration date. If you, I don't know, I believe once I checked a certificate, I don't remember, was it USG.edu or some other university, and I think the expiration date was by 2020 year. So they just say, let us just purchase it for years. Any questions? Now what we're going to discuss is what is the certificate and how can we make all these CAs, all these certificates, certification authorities or agents, to coexist. Because if we just say that each of the CA is independent, that's so many synchronization between CAs needs to be applied. So in other words, say one CA issued certificates to one set of websites, another CA issued certificates for another set of websites. Because we, the owners of websites, choose the certificate, the certification authority. We choose them. In other words, some people can choose CA1, some people can choose CA2. Right? What if now users of CA1 wants to communicate with a resource certificated by CA2? Previously, we were assuming that all public keys of all CAs are on web browsers or on the operating system image. That is correct, but if you try to think of implementation of this idea, it's probably problematic. And problems come from the scale of this environment. It's not a problem if we have only 2 or 3 or 4, but if you have 1,000, and if you want something which is called cross-certification, you're eventually going to see issues. So let us first look at the content of a certificate, and then we'll see how cross-certification may work, how cross-certification may help us in scaling up this infrastructure. Scaling up meaning that we want to have as many servers as we want and as many CAs as we want. Yes?
Is that the same thing as doing the cross-realm from Kerberos?
Pretty much the same. But with the cross-realm concept in Kerberos, it is flat structure. In other words, the hierarchy has only one level. All realms are connected by together. With the CAs, and I will show you very soon, with CAs you may think of a tree, hierarchical structure with many levels. On page 431, if you have this edition of the book. If you don't have this edition, look for X509 chapter. So X509, this is the standard for certificates. And this is just one of the standards. There exist some other ones, but this is what is used in the internet for certificate exchange. Actually, to form the certificate and to describe how they can be exchanged, issued, revoked. And on page 431, you can see a diagram that shows content of the certificate. And let me just draw this diagram for those who don't have a book today. So there is version field, serial number. There is signature algorithm. Period of validity and subject name. Public key. So this is the structure of X509 certificate. We're talking about different versions of certificates, and it could be 1, 2, or 3. The higher the version number, the more fields are there, and you may find a diagram in the book that everything up to issue unique name, issue unique ID. So this is the scope of version 1, all the way down to extensions. This is version 2, and everything is version 3. And actually, this part is for all versions. Serial number is a unique number of the certificate in the database of certification authority. So serial number is unique only in the scope of all certificates which were previously issued and will be issued by that CA. In the internet you may find two or more certificates with the same serial number, but it is possible only if those certificates will be issued by different certification authorities. So serial number is local for a CA. Signature algorithm, it's what is duplicated on the last block. This is what type of asymmetric key algorithm is used. So far we've just learned only RSA, but RSA is not the only asymmetric algorithm. So not necessarily RSA is used for digital signatures, but there is a very high chance that RSA is involved. Issuer name, that's our CA name. And this is written in plain text, in readable text, like VeriSign, RapidSSL, well, whatever name of that business is, it will be listed here. We'll also later have issuer ID, so that's the number. That's the number that uniquely identifies the name, because it's probably not a good idea to uniquely identify CAs by name, because name can be written in different ways, and just making one letter capital or small or placing one extra period in the name will make the difference. But in terms of numbers or identities, I think it's either number or hexadecimal number. Then uniqueness is easily maintained. So issuer name and issuer ID just to identify the CA. Period of validity is defined from to. From should be somewhere in the past, to should be somewhere in the future. So if we've got a certificate, say, from a website, we want to make sure that current time is somewhere in between. If current time is here, meaning that certificate is expired. If current time is here, which is very odd, it is also possible, but that's probably we'll see if you move your system clock 1 year back. Certificate also, in this case, will be found as invalid, and you will not be able to use it. Normal situation, this is abnormal. Subject name, it's what your web server, the way how your web server is identified. As I said, certificates are not only good for web services. They can be good for mail exchange, they can be good for file transfers, for many other reasons. Many other infrastructure services rely on certificates. So subject name in the context of web services, it's something like gswcm.net. That's what we've got for our subject name. Subject name could be, I don't know, gsw.edu or rain.gsw.edu, because gsw.edu website does not require any data encryption, but rain.gsw.edu does require encryption. Public key, it's not only the key value, but also the algorithm used and parameters of that algorithm. What kind of parameters we know? It is not n parameters. All right, let us talk about public key in more details. Public key in RSA, it is two numbers, E and N. So that's the value of the public key. But the two values are not necessarily RSA algorithm. So type of the algorithm is also listed here. If we say this is RSA algorithm and there are two numbers, what else do we want to know about the public key so anybody can use it? Public key and two numbers, N and E. I'm sorry, RSA algorithm and then two numbers, N and E. What are we missing still? Looks like it's sufficient to use it, the public key. In fact, when we're dealing with real use of RSA algorithm, we want to know how big is the biggest number. And with RSA algorithm, usually number E is fixed. So number E, I think it is 65537. Probably it is the same number for each and every certificate for each and every case. What gets changed is number E, number N. Number N is different. So range of changes, range of potential values for number N, it's one of the parameters that also needs to be stored here. And when we had a discussion how big are those numbers, N, I gave you an example in Wolfram Alpha with just bunch of characters, bunch of numbers, bunch of digits to form that number. And eventually it wasn't sufficient, so Wolfram Alpha can break that RSA key. Breaking RSA key is nothing more but factor out this value into two factors, into two numbers which appear to be, after being multiplied, are equal to N. If the number N is too big, then we can break it into two factors. So with number N being too big, we need to know how big is the biggest N possible. And we limit it by in form of binary numbers. So usually we say 2 raised to the power of 2 all 48, for example. In this case, we're talking about 2048 bits to represent number N. So if this is the number of bits to store number N, wherever number N we're going to use in reality will be as close to that number as possible. It is obvious that with 2048 bit you can represent number 7, or you can represent number 13, or in case of N to be a product of the two, we can say number what will be, say, 143, the product of 13 and 11. Number 143 can also be represented by this range. But we do not declare the range to use its left side. We declare the range to use its rightmost side, where the biggest numbers are. In other words, we want to choose a few numbers which are close enough to this value, but do not exceed it as number N. But 2024, 2048 is a parameter of RSA algorithm, and it needs to be listed here. So that's what we list for public key: the algorithm, parameters, and key value. Issuer ID, and we already talked about subject ID. I told you that subject name is identity of our website or identity of the mail server or some other type of identity, but something that humans understand. Why humans need to understand subject name? Because when a person is exposed with a certificate, it wants to see that this is the certificate issued to this particular resource. If if we try to access Facebook, but we can see certificate issued for Google, how it's possible? It doesn't make sense. So when we see the certificate, you always will be able to identify the name and identity. But identity is just a number. It is stored in the database of CA. Because each and every certificate that CA issues is stored on that side, on the CA side. And that's only for tracking purposes. It's easier to use that number to locate a certificate, but subject name, probably it's not that easy. It's local business of CA, in other words. The extensions that, for example, what makes it possible to use a certificate for not only for web browser, but say for some additional tasks. For example, if you have a network infrastructure and want to encrypt data not only from web browser to a web server, but between two arbitrary processes that use sockets. Socket data exchange or socket-based network data exchange, it's a common situation. So if you want to build up a security application that also requires data encryption, you might think of using one of the extensions that will allow to use the same certificate for that software. We probably want to skip this part because we have so many items yet to discuss. But extension, this is what makes possible to use the certificate in non-standard or non-trivial applications. And digital signature is actually what we are mainly interested in terms of protecting data of certificates. The way how digital signature is stored, again, it's similar to the public key. It's the algorithm, parameters, and value of the signature. But what is important, digital signature is not applied to the raw data of the certificate. The raw data is like numbers, characters, and everything else. It is different in size, right? It is different in content. It spans many different characters and many different numbers and whatsoever else. So we do not calculate digital signature over raw data. We first calculate hash of this information. And hash, this is what I introduced a couple of classes before. Hash, it's a function. We'll be talking about hashes also, probably today. Hash is a function that can be fed with arbitrary information, but hash value, it's always of the fixed size. So you, for example, can calculate MD5 hash over file of any file. Doesn't matter how big is the file. Doesn't matter what contents it has. So MD5, actually usually they say MD5 checksum, not hash. But hash has pretty much similar idea. So hash or checksum, it will have the same number of characters, the same number of hexadecimal characters usually. Why do we need this? Because digital signature in this case will be applied to the same number of characters every time. Size of the digital signature will be fixed. If we apply digital signature over the raw data, size of the digital signature will depend how large is this collection of data. But if you apply digital signature over fixed amount of data, then size of the digital signature will be the same. this is convenient. Any questions? I really encourage you to read a couple, probably it's 5 pages just about certificates. The public key infrastructure chapter in your book, it's beyond the scope, just the scope of certificates. And it discusses how certificates get issued, how they get revoked, and whatever we discussed today already. But it's always good to read kind of the same idea in alternative words. So read this information, but try to go slightly beyond the level where certificates are discussed. For example, there is a section 14.5 in this edition. It's called public key infrastructure. That's what we discussed today. But they discuss not only how certificates work and whatsoever, but actually a real application of the certificates in the internet. I mentioned that nobody is using public key to encrypt all data because it is just waste of resources. So public key infrastructure chapter, actually section, discusses this approach. And if you want to be kind of familiar with how internet works with that certificates, you want to take a look to SSL. SSL, it's abbreviation standing for Secured Socket Library. Sockets is a mechanism to provide networking feature in any modern operating system. It came from the Unix world, but nowadays it is adopted on every operating system. In Unix-based operating system, it's part of the system library, but in operating systems like Windows, it is implemented as a standalone library, like add-on library functions, not part of the operating system. But it's not important. What is important is that pretty much every computer in the internet, especially in the consumer market, communicates with other ones by means of socket library. Secured socket library, it's extension to it. And secured socket library allows you not only to send data between applications, but also to apply data encryption. So SSL, in turn, that's very big subject to be discussed. We don't have time for that. And if you think of just identifying components of SSL, X509 is just one of the components. Other components are, for example, symmetric encryption algorithms that are used to encrypt data, and different approaches to encrypt data, different algorithms, different, I don't know, practices. Recently, more than likely you have heard from the news, there was hard bleed SSL attack. What was that? SSL library, it's a standard. Standard, it's not what we have in terms of software. In terms of software, we have implementation of a standard. And OpenSSL, it's open source implementation of the SSL library. of the SSL functionality. This has just happened that many computers in the internet nowadays use OpenSSL because it is open source. Everybody can download this library and start using it for their own applications. You don't want to implement encryption or decryption for your own application. You just want to use the library to be so your application, the one that you develop, can benefit of already implemented solution. OpenSSL is not the only SSL implementation. There are proprietary implementations. Those did not suffer from the Heartbleed attack. Heartbleed actually is not an attack. It's the issue which was discovered by programmers. It is not like every computer which had OpenSSL was attacked. It is a threat that every computer with certain version of OpenSSL library can be attacked. So there is a procedure. If you follow that procedure, you actually can, the attacker can access your private key. That's how private keys can be compromised. That was the recommendation for all system administrators. If your servers are built around OpenSSL library, you want to update the library, otherwise private keys of your web servers or private keys of some other resources can be compromised. And you never know, as system administrator, whether or not your private key was already compromised. So the suggested activity was whatever private key you have is bound to a public key, right? Public key is bound to a certificate, X509 certificate, which was issued to you by certification authority a while back. Assuming that your private key could be compromised somewhere in the past, you want to replace the private key, meaning that your public key and certificate become invalid. So you want to restart the process of certification for each and every resource you have. So in other words, the two things, minimum two things, every system administrator in the world who was dealing with OpenSSL had to do. First of all, install the patch for OpenSSL library that addresses that issue. And second of all, get the new certificates for each and every resource you manage. And say if your infrastructure shows 10 servers, web servers, that's probably easily doable. If it shows 100 servers, it needs to be applied on each and every one. Because when you're dealing with certificates, you actually want to generate a pair of public and private key. You want to send a request to CA and wait for CA to approve your request, because CA needs to know that you are the same person who has purchased the certificate in the past. You paid for that service. And every person who already paid for that service can request the new certificate, because private key of that person could be compromised. They do not require you to pay, but it is still time for CA to respond to you. And usually they say it is 24 to 48 hours. In reality, it takes just a couple minutes. But assuming that everybody in the world will try to reissue their own certificates, I think it was the rush time. And when certificate is issued back, you want to install it on each and every web server. Installing of the certificate is nothing more but to copy a file into a particular location, or to run in a certain program and then browse for that file and then say install the certificate. It's a trivial process, but it needs to be repeated over and over again on each and every browser. So X509 is just part of SSL. If you want to learn more, look for SSL. But I'm telling you, this is just huge amount of information to be read. Part of this material, you might think of, for example, procedure between client and the server. In case of web browser, it is a procedure between web browser and the web server to retrieve the certificate. We easily say that web browser requests a certificate from a web server. But how does it look like in terms of messages? So SSL describes those messages. How the request looks like. How response looks like. How do we trust to the response? What if we send the request but response never came back? Alright, we send the request, response came back. We've got the X509 certificate from there. What next? We want to use the public key to encrypt some data. And I told you that we use public key from the certificate to negotiate, actually to deliver the symmetric key of some exchange algorithm. So that's another process. And that process also described here. For example, one of the applications of SSL, it's secured shell. We use secured shell to access any Unix server. SSH, if you want to connect, you want to have SSH server and SSH client. SSH server is installed on Unix machine. SSH client you can run on any operating system. You can run on Windows, Mac, Android. Any device can be equipped with SSH client. So SSH server, SSH client. For some reason, I don't know what were the real reasons, but the very first version of SSH was developed to allow plain text. In other words, no encryption for username and password. It is called secured shell. The data later on will be encrypted, but username and password were not encrypted. That's one thing. Then they discovered this and they issued the version 2. Version 2, which is nowadays a recommended version to be used about SSH. So if you install SSH server, you want it to be version 2. But what should we do with those clients who do not support version 2? We want to allow them to connect to us, or do we want to reject them immediately? If we do allow them to connect to our server, at least we want to tell them, hey people, this is not secure to use version 1 anymore. Consider updating your client. But the way it works, we want some form of communication, some form of negotiation. For that purpose, they developed version 1.5. 1.5, it's actually not the version that of the protocol for data exchange. It's mainly the version for negotiation about the version later to be used. And it works as follows. Client never knows which of these two versions are implemented on the server side. So client normally sends a request to the server. I want to start secure communication with you. Request. Server wants to ask a question. What version do you support? Client can say, I support version 1. Potentially it may support version 2 as well. So if server can see version 2, it says, all right, you support version 2, let us support version 2. And then the real data exchange. It's not involvement of version 1.4. This is kind of good communication. What will happen if situation is still under control but not in that good shape? A client still sent a request, and server doesn't know what version client supports. So previously we were saying server asks a question, but server wants to, in one message, address all the potential questions later on. It tells the client, I support version 1.5, meaning that it supports both versions. Right? Client can see this, and it's going to say, as long as you support both versions, let us stick with the 2. All right, let us stick with the 2. I'm good. Right? Now, if you think of this message exchange, what message do you think attackers would like to modify to degrade version of SSH back to 1? Degradation of the version, this is what attackers wants to do, to make sure that after this negotiation, client and server starts dealing with version 1, which supports no encryption for username and password. Because if these 4 steps will end up with version 1, then later on, non-encrypted password and username will be sent. So, in other words, if we're still talking about presence of Cathy somewhere in the middle, and that Cathy, by the way, this negotiation cannot be encrypted, because it's not, neither client nor server shared no secret yet. Secret is shared here, after version is negotiated. So all these messages are sent in plain text with questions and answers. Request send. Server responses, I support version 1.5. We intercepted this message and we break the delivery. Now we say, I support only version 1. Client can see it. Okay, you support version 1. I support 2 versions, 1 and 2. No, you don't support 2 versions. You support version 1. Okay, server gets this information. Client supports only version 1. It is now policy of the server to accept or to reject it. And server, if it decides to, so it's actually a line in the configuration file that tells you only version 2. If it is not only version 2, then server sees only version 1 is supported. Alright, let us do version 1. Okay, version 1. I support both, but server said version 1. Let us do version 1. And then encryption key for data, but password and username without. So these 4 messages is described here. That's one example. Yes. Want to go?
Yeah.
All right.
But then does that come with it if you make a, if you have like an account with someone and they tell you you have to make like a backup password or you forget it? Is that the same kind of thing? And sometimes they'll be like, your mother's maiden name, like that.
This is same idea when you're talking about secret questions, that type of things, right? And that's the way for you to recover the password. So let me start from asking, what for do you use the password? To be authenticated, right? A person who is not authenticated is not rejected to use encryption. So now we're talking about encryption. If you're talking about somebody to be able to guess answer for the security question, it's a different story because it is on the higher level. Here we're talking about very low level where actually data are encrypted. If anybody can guess your answer for the security question, then yes. But that's actually our abstraction where service providers want to carefully formulate the question. This is where they not only want to, for example, to limit their service with a security question, but for example, to display image that some of the web browsers or some of the banking system nowadays are doing. Some other tricks. Maybe you want to use similar technique as Google is doing with their authentication application and other ones. But it's not related to encryption. It's more related to data processing, to data management. So many times we were talking about Kathy who can read data, who can modify data, who can block delivery of data. But how it is possible? It is possible mainly by knowing the way how networks work. Because networks should not be considered as just interconnection of cables. You want really to understand where these cables are plugged in and how data propagate not only through the cable, which we're actually not going to touch. We'll be touching the computers and devices where cables are plugged in. Because we don't have any equipment, and many hackers do not have equipment just to stay around the cable and put some device on top of the cable and then be able to read the data like we can see in the movies. They just put some clip on the cable and immediately all the data are here. I don't know if it's possible or not. I doubt that this is possible, but we're not going to follow that way. What we're going to do, we're going to consider a topology of a network from the perspective of ability of one part of the network to be able to get access to another. That's actually what we are what we are assuming when Alice and Bob are communicating, and we say that Kathy is somewhere in the middle. But think in terms of real network topology. Alice and Bob never have direct cable in between the two. It doesn't make sense for them to have a direct cable because in this case, if we want some other parties to participate in the same network, then we want to talk about cross connectivity. Cross connectivity, it's not the best thing to do, first of all, because each one will need many adapters, many network adapters, and second of all, there will be unpredictable complexity of the network when number of nodes will increase. So this is not the solution we adopt. We adopt a solution that in best can be described by switchable networks. Actually, it is not networks which are switchable. Word switchable is related to packets. So network packet is switchable. And what does it mean? A packet to be switchable. A packet is just sequence of bits. Sequence of bits that traverse the network, and the switching actually takes place in devices that decide what will be the next destination of the network or of that packet. So in other words, we're no longer talking about direct communication of two computers. we're talking about some device which connects two or more computers. How many devices can be supported? As many as network capacity is. And what is this network capacity? What is this measure? Can we say that in one local area network we may include 1,000 computers? Yes, we can. Can we include 1,000,000 computers? Yes, we can. But 1,000,000 computers will communicate less productively compared with 1,000 computers. In this case, if we want really 1,000,000 of computers to be communicating one to another, we want to break this one big network into sub-networks and then organize routing. So routing is the process of interconnecting multiple networks. And this is what Internet is all about. Internet is interconnection of multiple networks, of many networks, and routing takes place constantly. So far we are talking about switching and routing. And actually routing is not possible without switching. But from this standpoint we are talking about two different operations. For routing to take place, we also need to consider packets. But those packets are different from what we consider in terms of switchable networks. Let me just depict a typical network with routing facility. Say this is one local area, this is another local area network, and just at the edge of the two there is one more. We can say that at the edge of two networks there are routers. Some have switch. And we're also talking about normal PC computers. PC not from the standpoint of PC or Mac, but PC is just a computer, the end device. So computers are connected to switches. How these two routers are connected? These two routers are also connected by means of a switch. So there is another switch, and we may have another router here which will go to some other network. And switch is connected to a router, switch is connected to a router. So now there are three types of computing devices: computers, switches, and routers. And from this standpoint, this is nothing more but scaled down version of the Internet. Internet is just the same. It is different from the perspective of seeing more productive devices, more productive channels between devices. But conceptually, Internet is like that. And when we were talking about switchable networks or switchable packets, it is just to support the simple idea. For example, if we want to communicate this computer and that computer, this computer will create a packet that is data and some service information. What kind of service information we want to include in the packet? Somehow we want to make that packet to contain its final destination, because this computer knows where the packet is intended. He knows that it goes there. But when the packet will leave its source, it will be by itself. So it needs to contain its final destination. Not only its final destination, but it also needs to contain the source address. Because once the packet will come here, this computer will need to know where the packet came from. And now we need to decide the path. What will be the path? In our case, the path is pretty trivial. From here to switch, from switch to router, from router to switch, from switch to router, from router to switch, from switch to computer. There is just one path, there is nothing to decide. But in fact, process here, 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 and here are associated with a decision. Decision that is made by a device in terms of where to move the packet. For example, that switch, it needs to decide which one of these four interfaces a packet needs to be routed. It's not a router, and I'm using word routed not just to confuse you, but routing decision made by a switch, it is just a decision to understand which one of these interfaces needs to be used. How switch does know that packet originated from here needs to go here? Switch doesn't know this unless we equip the packet with that information. When we create that information, when we create that packet, somehow we need to put information that all outgoing packets must first come to the router. What is router from the perspective of that computer? It's yet another computer. A computer with its own address. So that address is known to this computer as the gateway machine. And gateway machine is used by this computer, and by that computer for all outgoing traffic. So we know its address. I mean here. We know that address. How can we inform switch that a packet, outgoing packet from here, needs to be forwarded to this interface? This is now decision by the switch to make, and this decision is made based on the address of the packet, which is contained in the packet, and address of that interface of the router. So when packet arrived here, destination address is extracted from the packet, and switch consults what is the address of the device which is connected to that interface. What is the address of the device connected to this interface? What is the address of the device connected to this interface? And if two addresses match, address from the packet and address from the device, then it decides that it goes to this interface. For the router, it's quite different situation. It has only one side and the other side. So for the router, whatever packet it gets from one interface needs to be forwarded to another interface. But router may have not only one interface, not only two interfaces. Router may have many interfaces. In this case, approach is the same. And approach is also to analyze the packet for the destination address and see how this destination address can be used to decide for the correct interface to use. So, in other words, on those supporting devices like switches and routers, we perform the same action. We make a decision where next we want to forward the packet. So what's the difference between switches and routers? Switches are the devices that support communication within local area network. Routers are the devices that support communication in between or among local area networks. When we say so, we cannot allow the same device to be used here and here, because it is different types of decisions they make. The decision made by this switch is trivial. It is one of the ports, and destination computer is connected directly to that port. So in other words, address in the packet is address of the device directly connected to the switch. But the router, when the router makes a decision, it doesn't have the destination computer connected to this interface. Destination computer is somewhere far away. So router makes a decision by using different mechanisms. And the first decision router makes, it's, for example, if it has two alternative interfaces. It knows that this interface leads him to that router, and for example, this interface leads him to that router, to another network. From the address of the packet, it may find out that destination address more than likely is in this network rather than in that network. So in other words, a router does not care at the point of making decision about final computer, final destination. It cares more about network where this computer resides in. And when it chooses for the network, it has several alternatives to consider. And without digging deep enough into how routing works, the idea is straightforward. One of the destinations will be chosen. Yes?
So if it decides to send a packet through the wrong line,
There is a chance that these two networks are also connected. And with the internet, with the concept of internet, we never know what will be the path for a packet. We can send a file comprised from multiple packets. One can go that way, another one can go a different way. And if you know what the model of TCP/IP stack of protocols is, or sometimes you may learn the OSI model or some other ideas, but basically any computers in the internet, any computer in the internet, any device with network capabilities can be represented as a stack of layers. Stack of layers that it's abstraction. It is not like we have 5 programs to represent each computer. This is abstraction. That's what you want to think of every computer in the internet. And those layers allow for data processing from the very top level where you have your application. Say your web browser. All the way down to the physical layer, where the voltage and current and cables do exist. So physical layer of this computer is connected to the physical layer of the switch. You may think of connectivity between physical layers of two devices. It's actually extension, that's the cable. On physical layer we deal with cables, on physical layer we deal with voltages. That's why we can connect physical layers. We cannot connect application with physical layer because it doesn't make sense. Application deals with more abstract data. But physical layer on this device deals with physical layer on that device. Switch can also be represented by a stack. But in case of switch, it is only 2 layers for the switch. Physical layer and the next one. The next one is called link layer. Switch doesn't run any applications. Switch doesn't network connectivity, which is addressed here. Switch doesn't deal with transport abstraction, where we deal with, where we operate with reliable or unreliable transfer. So switch only needs a cable to be plugged in somewhere and a link layer that considers a cable as a media to deliver data. In other words, here we have sequence of bits on the link layer. On the physical layer we have voltages. And in between the two there is a transition between bits and voltages. And as long as internet allows many different types of physical layers, so what you used to think of a network, it's just a network cable, it's just one type of the network cable. Years ago there was different type of cabling, coaxial cables. There exist fiber optics cables. There exist radio frequency channels. There exist radio frequency channels to the satellite systems. All these are physical layers. But all these layers, all these devices, must be switched here. We cannot say that, for example, between switch and a computer, there is a link represented by a satellite connection. Because satellite connection requires some other layers to support this communication. First of all, because there is a high possibility of errors and not all packets are going to be delivered. They must be retransmitted. So that's the purpose of the higher levels. If certain packet was lost during the transfer, it is detected here, but link layer is not necessarily the layer which makes a decision for retransmission. Sometimes it needs to postpone responsibility to re-request a packet to the network layer. Network layer can postpone responsibility to re-request the packet to the transport layer. And finally, application could be the end point that makes the decision that certain packet needs to be retransmitted. So that's why we do not think of this link to be represented as some fancy communication. Usually it is as simple as it can be, Ethernet cable, the cable that you used to think of network cable. So switch is a kind of primitive device that gets the packet from one device connected, and then it finds out where this packet is going to, and then moves it to a particular port. And then this port, this interface of the switch, is also two layers. So these two layers is not just for the entire switch. These two layers are for each interface it has. And link layers are connected. So in other words, we think of a switch as one big link layer and then multiple physical. Each one with its own cable. You can also think that these are just different link layers and then there are some sort of communication. But as I said, this is abstraction. You might think of just one big link layer. You might think of many other ones, many other ones which are connected. The point is, the link layer is responsible for decision where the packet is going to. And this decision is made based on address. What type of address we have on the link layer? MAC address. MAC address is media access. Don't remember what C stands for. So this is the hardware address. This address is what you may find on each and every computer, regardless to the fact where this computer, in what network this computer is working. This address is always with that computer. If you move that computer to that network, MAC address will be the same. So link layer deals with MAC addresses. Switch deals with MAC addresses. And switch somewhere in the memory has the table which makes association between MAC address of the device with a port where this device is connected. And when it sees MAC address, destination MAC address from the packet, it just knows immediately where this packet is going to. From the table, it can find out the port number, and then it pushes that packet to the port number, and then look what's happening. There is a physical interface bound to that port number. Physical interface is now responsible to translate packet into voltages, and voltages happen to be here. That's how switch works. How router works in turn. Router has 3 layers, because router must be responsible for the network, not for the local delivery, but for the network. Decision made by the router is way more complex, because it is hard to say which one is the correct. We can say one of them is better, but always when we say better, we want to say in what way it is better. That better can be less number of hops between the router and the destination. It can be one strategy, less number of intermediate connections. Another strategy could be the fastest delivery. Delivery will be the fastest, not necessarily if it goes through less number of connections. It may go through greater number of connections, assuming that each connection is faster. So now we're talking about different properties of each of these links. That link could be as slow as dial-up modem with 57 kilobit per second. Or it could be as fast as fiber optic media, which is 10 gigabit per second. 10 gigabit per second. If one of the paths assumes 100 links, but each of these links is fiber optic, compared with 10 links and each of them is dial-up modem, probably choosing the longer path is the better option. So the router never makes the decision which is correct one from all perspectives. Switch does make the decision, because particular computer is connected to particular port. That's why we want to include network layer to support router operations. Network layer deals with networks, the final destination, but not a computer, not from the computer standpoint, but from the network standpoint. And when the router makes this decision, it uses different type of addresses. Address not that uniquely belongs to a computer, but address that temporarily belongs to the computer. Address that identifies a computer not only within the network, but in the entire internet. That address is called IP address. The second type of address, MAC and IP. When we're dealing with IP addresses, IP address is registered on the network layer. Also, we may have source, destination, source IP address and destination IP address. And now it is the question how these two addresses are associated. How they, in what way they are similar and in what way are different. As I said, one same computer we always have the same MAC address. But one same computer, depending on which network it is plugged in, may have different IP addresses. So in other words, IP address, it is a matter of configuration of particular network. If you bring your own laptop here in this classroom, you will be connected to one network. If you plug in your laptop in library, it will be different network. But from this network, you can access computer in the library. That is possible. What will be the direction, what will be the path from here to there, it depends. Depends on many issues. We do not discuss this. What we're going to discuss is how attacker can read the data. Because looks like if this is Alice, this is Bob, where attacker can be. If attacker is sitting, for example, here, what is the chance that attacker will get access to the data? It is not possible because there is a very high chance that data will not even touch that network. If data do not touch that network, attacker will not get the data. So where do you think attacker needs to be present to be able to access the data? Either here or here. Right? So if attacker is sitting here, we say attacker has physical access to the network. And that's another assumption. Attacker needs to be able to be into the same switch. Because this is the at least sort of guarantee that packet will go through the device where attacker has access. The only thing attacker needs to do now is trick the switch. So packets do not go here and then here, but packets need to go here, here, return back to switch, here. That's what attacker is interested in doing. How this is possible? Why, for example, packet which has particular destination will be routed by the switch not to its destination but to the attacker computer. And this is called man-in-the-middle attack. First of all, we make some change in configuration. But it is important to understand where this change is applied to. Switch is a piece of hardware. We do not plug cable out and plug another cable in. Say, when we detected a packet going here, we do not plug ourselves into that jack, into that socket. It will never work because packets, there are so many packets. What we want to do, we want to trick that device. We want to attack the computer, not the switch. And computer will actually include wrong destination address into the packet. The intent of the computer, of some software, say if we want to communicate Bob, will be to have the destination MAC address of the router. In fact, we will make it, attacker will make it, the destination address, the destination MAC address of packets to be our MAC address. In this case, switch will just do the job. It will push the packets to us, and then it's up to us to decide where do we want this packet. We still want Bob to receive this. Maybe in modified way, maybe in modified form, maybe in the same form. But this is us to decide. So we push the packet back to the switch with the correct destination address here. What do we do with this packet? It's again up to us. We can keep it intact or we can modify it. If we modify it, data in the packet will be affected. If we do not modify it, this is just normal sniffing. So modification of data or sniffing of data. It is decision we make once we get control over the packet. And the last question, how do we trick that computer to send us the packets when it wants to send them directly here? That's the question that we'll consider on the probably last day of the presentations if we'll have time.
Is that what we talked about per se spoofing?
Spoofing is different. Spoofing is that you change your MAC address to pretend that you have MAC address of the router. Yes.
Can you tell us that?
To do what?
I want to know how they're.
How? All right. We have a couple minutes, and
I'm sorry, y'all.
it's the only reason for me not to start this conversation now because it will take us long. But let me just briefly show you the way it works. Let me simplify that circuit. Say there is Alice, and now we're talking about just one local area network. There is Alice, there is Bob, here is the switch, and here is Kathy. All right, each one has MAC address, MAC 1, MAC 2, MAC 3, IP 1, IP 2, IP 3. And switch knows that this port is for MAC 1, this port is for MAC 2, this port is for MAC 3. It is important that switch doesn't deal with IP addresses, only with MAC addresses. Now, what A needs to know to be able to reach B? Can we assume that A knows MAC address of B? Not a chance, because this is the part of the hardware. We never know what is the other computer, what is the MAC address, what is written on the label, which is sticked somewhere in the case of the computer. We never know MAC addresses, but what we know, IP addresses. IP address is the logical thing, which can be reassigned at will. So A knows IP address too, but to contact B, it needs to know its MAC address. There is a protocol called Address Resolution Protocol, ARP. This is the protocol that explains what we need to do from A side. By knowing IP2, how can we find out MAC address 2? And the idea is straightforward. We start broadcasting a question. Who has that IP address? Who has IP address IP2? That message is broadcasted. Broadcasting is a special mechanism that will be received by the switch. And switch will identify that this is broadcasting. It will send it to each and every port. So everybody in our local area network will receive that message. But only computer that has that same IP address that is contained in the question will respond. And it will respond with the value of his MAC address. So MAC address will be sent to switch, and then how do we know where switch needs to deliver this response? How do we know that the message was sent by A? The question was sent by A. Any packet has source and destination address. We made destination address to be broadcasted, but source destination address, but source MAC address is address of A. When we send out the broadcasted message, and eventually it comes to B side, it reads that the message was sourced from A. Now it uses MAC address of A, which is MAC 1, as the destination address to send the question, the answer. So now A receives a message that MAC address 2 is associated with computer B, and it stores it in the memory somewhere. It has IP address, small table, IP MAC, IP2, MAC2. If we have more than one computer to communicate, it will have IP3, MAC3. Doesn't matter that this is our attacker. Kathy can pretend to be a normal person. So this is the table maintained by A. Similar table will be maintained by B. IP MAC. But B doesn't need to know his own pair. B needs to know MAC address 1, IP1. IP1, MAC1. And IP3, MAC3. And Kathy will have IP1, MAC1, IP2, MAC2. What happens next? It still doesn't help Kathy to do any sniffing, because now if A wants to contact B, it knows IP2, it knows IP address of B, it reads the table, it finds out MAC address 2, it uses that MAC address 2 as destination for the packet. Switch receives a packet with destination MAC2, it forwards it here. Everything looks good. But what Kathy can do, what do you think Kathy can do?
Look at her table and switch it to her computer to MAC2.
But looking the cable and switching, you see, Kathy just doesn't have access to that cable. That's important, because that's how switch works. Forget about all our assumption that Kathy can do everything. Now Kathy is plugged into her own port. The only chance that Kathy will receive a message if that message will have Kathy's MAC address. That's the only chance now. What if Kathy will wait for Alice to broadcast that request that Bob's supposed to reply? Now, Bob replies with the correct answer that IP2 is associated with MAC2. And Kathy will reply that IP2 is associated with MAC3. So there will be two replies to one same question. One of these replies is good one, other one is not good one. Other one is correct, and other one is incorrect. Both of them will be redirected by the switch to that port, and both of them will be received by A. Depending which one will be received, the second will be stored in the table. So there is a chance that MAC3 will be stored in that table. How Kathy can increase that chance? What if Kathy, upon listening to this broadcast request, will reply not just once, but many times, just to make sure that her message was delivered and stored by A. And now A has IP MAC3, same with Bob, IP1 MAC3. What they will be doing now, A wants to contact B, A knows IP address, oh, that's MAC3. Boom, boom. The message is here. And then Kathy just wants to forward it back to Bob, so Bob will receive it. The question is, why activity of Kathy is allowed, such activity of Kathy is allowed into this network? And the answer is simple. When network was developed, it was developed for scientific environment and for military environment. Security was at lower priority. But the same protocol that was invented 30 years ago is used nowadays. It's just because ARP protocol is not protected. It doesn't assume any sort of authentication. What we're missing is actually a response when we send from Bob. There is no chance that A can validate that this response is correct. It's from the correct person. There is no authentication. If there was authentication for that response, then Alice will reject everything that comes from C. But will accept only those responses that come from B. That's the key. And you as potential system administrators, what you want to do to protect against this type of attack, what will you do, by the way? Find key. Sometimes Kathy just looks normal person. You shouldn't just shut down each and every girl.
You just go all taken over.
So in other words, you don't know who is Kathy. You cannot identify her just by looking her working on a laptop. But what you can do as working here, because this is the end user, this is the end user. System administrator usually can monitor the switch. And when he sees that switch receives multiple replies to ARP request, attack is in place. So that's the warning system administrator receives, that something goes wrong. And now system administrator needs to know who is doing bad things. How can he know this? For example, what system administrator can see is that there are two responses to the same question. One of them comes from Bob, another one comes from Kathy. How system administrator can identify that this response is good one, this response is not good one? So that response will contain correct IP address and MAC address. Somewhere system administrator may have a record that this is the real IP address and MAC address association. In this case, by observing two responses, two replies, administrator can identify what is the MAC address of attacker. Knowing MAC address of the attacker, administrator may identify IP address of the attacker. Also from the same database, which we call DHCP server. So somewhere IP addresses are usually assigned automatically based on the MAC address. And that information is logged and stored by system administrator. It is available. So we can identify MAC address, and then we can find out what was the IP address, and all right, here is you. Here is the port in the switch where cable is plugged in. So where is the cable? Boom. Here is the person. That's one thing. Another thing, educate users. User probably is not even aware that ARP protocol is working. How many of you have heard of ARP protocol? 2, 3, 4. What's the chance that non-computer science or IT people are aware of ARP protocol or this type of attack? Very little, right? So normal users have no idea about it. But normal user can install a piece of software that system administrator can give to him. And this is not just antiviral software, because this is not a virus. It is not a malware software, anti-malware software, because it is not a malware. What is happening, people, or Kathy in this case, exploits the weakness of the protocol. She does not infect your computer. Your computer is not infected. Computer is just the same state of the computer, the same set of software. It is not detectable by normal tools. But what you can do in terms of writing a software to detect and prevent this type of attack, it's to write a software that accesses that table. And what we are looking for in that table? 2 records with the same MAC address. 2 or more records with the same MAC address. If we can find 2 or more records with the same MAC address, that's the MAC address of the attacker. So automated message can be sent to system administrator, then here it is. Go find him.